Today I'm going to look at a field design question, and the question is asking a simply separated beam shown in figure 1 supports the uniformly distributed load unfactored, dead, and imposed load of 5 kN each, as well as unfactored imposed load of 30 kN at midspan. Single beam is fully restrained at support. Select a suitable QB section in grade S275 steel to satisfy bending, shear, and deflection consideration. Ignore the beam self-weight and take E as 205 kN per meter squared. So this is the figure. That's figure 1. The span of the beam is 10 meters with 30 kN imposed load at midspan and 5 kN dead and imposed load. Before we start calculating or solving this question, we can look at the summary of design process of the beam. So the first stage is to design, check for shear force SV and bending moment M. The next step is to do what is called the initial selection of the U-beam. Then, to avoid bending failure, it is necessary to ensure the design moment M does not exceed the moment capacity of the section that is MC. That is to say, M should be less than MC. The next step is to classify the section. Then we check for shear, then for bending, and finally we check for deflection. Let's start with the first stage, that is calculating the shear force SV and bending moment M. So the design load is given by the formula 1.4 GK plus 1.6 QK. 1.4 and 1.6 are the partial factors of safety. GK is the dead load, and KQ is the imposed load, also known as the live load. So if you work out that, you get 1.4 times 5. All right, 5 is the dead load. We only have one dead load. That is the UDL. Okay, this one, the one I'm pointing with my mouse. Then you have 1.6 times 30. That is the point load, this one. Then you also have the UDL of 5. We multiply by 10 to convert to get the total load. All right, it's 1.6 times 30 plus 5. That is the imposed load. UDL times 10. 10 is the span. If you do that, you'll get 70 plus 128, and you get a total downward force of 198 kilonewton. So for the reaction, since this beam is loaded symmetrically, you'll get that reaction at A will be equal to reaction at B, and it will be equal to 198 divided by 2, and that is 99 kilonewton. Next thing, we calculate the bending moment M. Remember, the formula for calculating M, we have two loading systems. We have the point load, the UDL. So it's WL over 4 for the point load. This is the point load. And this one, this formula here, is for the UDL, the uniformly distributed load. If we work out that, we get 48. How have we gotten 48? 48 is 30, the point load, times 1.6. Remember, this is the imposed load. So the factor of safety is 1.6. With 30 times 1.6, you get 48. The L is the span, you get 10. Then this 15, how have we gotten this 15? It is 5 times 1.4 plus 5 times 1.6. All right, we will get 15 combined plus or rather times 10 squared. 10 is the span divided by 8. Please don't get confused. I'll repeat. How have we gotten 15? 15 is 5, the dead load times 1.4, the partial factor of 50 plus 5 times 1.6. Okay. If you add the 2, you get 7 plus 8, which is 15. Okay. Times now 10 squared divided by 8. So for that, you'll get 120 plus 187.5, and you'll get the total bending moment is 307.5 kilonewton meter. So if you check now the bending moment diagram, this is the, so we start with the shear force diagram. This is the shear force diagram. We have a value of 99 at the support and 24 where we have the point load. So our highest value that we are going to use for designing is 99. When you're designing, you take the highest value. Then the bending moment will look like that with the highest value being 0.7. All right. And we will take the highest value for, right, for the highest value for shear force is 99. Okay, good. So now let's go to our second stage or step, and that is the initial selection of the U-beam. So bending is usually the critical component. So we usually check for bending. For when we are doing the initial selection, we use the bending moment. This is the formula where we get the Fx. The Fx is the section plastic modulus, and this will help us get a rough estimate of the beam that we require. So when you do that, I will say the Fx is the beam plastic section modulus, and the Py is the design strength of the steel, and M is the applied moment. If you do that, M is 0.7.5. Now, why have I multiplied by 10 raised to power 6? This is, remember the moment was in kilonewton meter. So convert to Newton, you multiply by 10 raised to power 3. And again, to convert it to millimeters, you multiply by another 10 raised to power 3. In total, it's 10 raised to power 6 divided by 275 Newton. So if you do that, you'll get 1.118 times 10 raised to power 6 millimeter raised to power 3. However, if you check the steel table, the value of Fx is given in centimeter. So it's important to note that the value of Fx is given in centimeter. We are going to convert this to centimeter, and we are going to divide by 1,000. If you divide this value by 1,000, you will get 1,118 centimeter cubed, right? So now if we check on the steel table looks something like that. And the plastic modulus, where I'm pointing, is given in centimeter cubed, same as elastic modulus and the other values. However, the dimensions of the beam are given in millimeters. So the first row here, we have the serial size. So I've taken the next factor of the beam, and remember our plastic modulus is 1,118. So when you're designing, you check for the beam whose plastic modulus is slightly higher than the required plastic modulus. In my case, I selected this beam for 6 by 178 by 60 U beam. So the 60 here is the mass per meter, and the rest are shown here. We have the depth of the beam, the breadth, the web thickness, the flange thickness, radius, and the rest. So for my plastic section modulus, Remember, we are looking for Fx. We are dividing along the x axis. So the value we're interested in is this one here, the one I'm pointing with the mouse, 1190, which is just slightly higher than the required Fx, which we calculated, and it was 1,118. Remember, you're also looking at the cost. So you don't want to take a beam section, which is heavier. Remember, steel is measured in kg. So if you take a steel section which is higher, it will be expensive. So we have to balance between the cost and the design requirements. So in my case, I hope this beam will be adequate, but we are going to check that. So if you want to extract the details of this beam, so we have said 5, 4, 6, and these are the section properties. So this one is just read off from the steel table. And the depth is shown here is 46.4. This is the breadth or the width of section. This is the small t is the web thickness. Then the capital T is the flange thickness, and the rest. So the Fx here is this one, which we're interested in, is 1190. And the Ixx, or the second moment of area of the beam, is the one shown here, the one I'm pointing with the mouse, that is 21,500. Remember, again, the section modulus, the second moment of area is also shown in centimeters to power 4. So now that we have gotten our section, let's continue and see whether our section will be adequate in bending, shear, and deflection. So first check, before that, let's go to step 3, and that's the classification of this section. This table is gotten from the BS 5950, and this is how you classify the section. It has 3 categories. So the beam can either be plastic, compact, or semi-compact, depending on this parameter. That is the ratio B over small t. If it is less than 9 epsilon. Now, how do you calculate this letter here? This Greek term is called epsilon, that looks like E. This epsilon is given by the square root of 275 divided by the design strength of steel, that is Py, and you get a square root. So in our case, the design strength is 275. So 275 divided by 275 is 1. The square root of 1 is 1. The value of this Greek letter here, epsilon, is just 1. So this is just a 9, and this is 80. If you look at our beam, the ratio B over T is 6.95. The one I'm pointing is the mouse. All right. Again, the ratio D over small t is 46.2. So our beam lies in this category. The section is class 1 plastic. All right. Let's continue. So the next thing is to check the shear strength, or whether the beam is adequate in shear. So in this case, the shear strength, the shear force FV should not exceed the shear capacity PV. That is to say that FV should be less than or equal to PV. How do you get PV? The shear capacity of the beam is given by 0.6 multiplied by Py is the design strength. AV is the shear area, right? So Py is 275. Shear is given by P multiplied by capital D. So now it's a matter of just substituting the value. 0.6 multiplied by Py is the design strength. T or T, you can read off from the table. Is here, the one I'm pointing with the mouse, is 7.8, right? 7.8. Our capital D is 406.4, the one I'm pointing with the mouse. Okay, if you work out that, you'll get it's 523 kilonewtons, right? Or 523 raised to 10 cubed newton, or basically kilonewtons. Okay, so our shear force, we had really calculated, and we saw the reaction, or the shear force at the support was 99 kilonewtons, and this is less than our shear capacity of the beam. Therefore, the beam is adequate in shear. So it has passed the shear strength test. Next check we are going to perform is the bending capacity of the beam. Is the beam adequate in bending? So to avoid bending failure, it is necessary to ensure that the design moment M does not exceed the moment capacity of the section. And in other words, M, the applied moment, should be less than the moment capacity of the beam. So the moment capacity is given by Py, that is the design strength of the steel, multiplied by section modulus, or the Fx. This one I have already calculated. Our Fx is 1190 multiplied by 275. You will get 327 times 10 raised to power 6 Newton millimeter. Now you have to convert this to kilonewton meter. How do you do that? You basically divide by 10 raised to power 6. Remember to convert Newton to kilonewton, we divide by 1,000. Then to convert millimeters to meters, we divide by another 1,000. If you divide by 10 raised to power 6, we get 327. So what was our applied moment? Our applied moment was 0.7 kilonewton meter, and our moment capacity is 327. So it goes without saying that this applied moment is less than moment capacity, and hence the beam is adequate in bending. All right, beam is adequate in bending. So the next check we are going to perform is deflection check. Deflection check. Now, BS 5950 provides deflection limits of various beams depending on what they are carrying and their loading configuration. For all cantilevers, the deflection limit will be the length divided by 180. For beams carrying plaster or other brittle things, the span should be span divided by 360, and all other beams except purlins and thick railing, the deflection limit should be span divided by 200. All right. So how do we calculate deflection? According to Morse theorem or Macaulay's theorem, these are the formulas. This is for a beam that is carrying a UDL. The deflection is given by 5 WL raised to power 4 divided by 384. For a beam carrying a point load that is at the center, the deflection is WL cubed divided by 48 EI. E is basically the Young's modulus, and I is the second moment of area. For a cantilever beam with a UDL, it is 4 WL raised to power 4 divided by 8 EI. And for a cantilever with a point load at the end of the support, it's WL cubed divided by 3 EI. Something to note that when you are calculating deflection, we use unfactored imposed load only. We don't use the dead load, and we don't factor the imposed load. So we use unfactored imposed load. Please take note of that. Take note of that. All right. So for our question, we had a beam that has to loading with a of a point, an imposed load of 30 kilonewton and an imposed load of 5 kilonewton. Remember, you're not going to use this dead load, and we're not going to factor this load. So this is the formula because the beam has both a point load and a UDL. So this for the UDL, and this is for the point load. So when we when you are calculating deflection, we calculate it in millimeters. Then, so to make our easier, so the first 5 is from the formula. The next 5 is the imposed load here, 5 kilonewton meter. So we have converted 5 kilonewton we have converted the length, sorry, we have converted the length to be in millimeters because we are calculating the section to be in terms of millimeters. So this 10 raised to power 4 is in millimeters. Sorry, we are just going to use as it is. We are just going to use the 10 meters as it is. So it's basically 10 meters raised to power 4. But towards the end, we are going to convert the meters, the deflection in meters, to be in millimeters. All right. So if you punch in the value, 5 times 5 times 10 raised to power 4 divided by, now 384 is from the formula. The value of E we were given, it was 205 kilonewton per meter squared. All right. So the value of I, is this one. And remember, the value of I is given in centimeter. So you have to convert to meters. So to convert it into meters, and remember it is 10 raised to power 4. You have to divide by 10 raised to power -8 because you are converting this to be in millimeter raised to power 4. So many students usually miss the unit. You have to harmonize the unit. If you are working with meters, it has to be meters. If you are working with millimeters, it has to be millimeters. So take note of that. So the value of I from the skill table was in centimeter raised to power 4. So you have to convert it to meters raised to power 4. And that's why we are dividing here by 10 raised to power 9. That's 8. Okay. Again, for the next formula, our W is 30 kilonewton. And that's why we multiply it's just that kilonewton. Then L cubed is the length. So you have to multiply 10 raised to power 3 divided by 48 divided by E. Our E was 205 times 10 raised to power 6. Okay. Divided by I. Our I again is 215, 21,500. You convert it to meters raised to power 4. To work out that, you'll get now the answer in meters. You get 0.0148 plus 0.0142 is equal to 0.029 meters. Now, if you convert it to millimeters, multiply by 1,000 to get to 10 millimeters. So, for our deflection limit, we are going to pick the third option here, span divided by 200. Our span is 10 meters or 10,000 millimeters. If you divide that by 200, you get 50 millimeters. So, our deflection is less than the limit. Therefore, the beam is adequate in deflection. So the beam has passed all the checks, so the beam is adequate. That marks the end. Don't forget to like this video, share, and subscribe if you haven't.